Hi, and welcome to USMA Orgo. We're now at Chapter 7, the first chapter of 2 on alkenes and alkynes. So, as we started the trend with the last lesson, usually when we start a new section, we're going to talk about introduction of physical properties, naming, and then some other intricacies about those functionalities that we're going to study. So, make sure you do the reading and understand some of the different physical properties of alkenes and alkynes. Pay particular attention on how to do E and Z naming, which is on page 292 and 293. And then the stabilities, because stabilities usually lead to trends and reactivities. So you can understand those trends if you understand the stabilities. So the first thing to pay attention to here is that we're going to start talking about synthesizing alkenes and then later alkynes. And they're mostly done by elimination reactions, which we just got done studying, so you should be pretty fresh in your mind, and you should be pretty good at it. But there's dehydration of alkyl halides, and then there's ways to make sure we get the E2 mechanism to prevail when, as you know, we talked last time, that there could be more than one route that a reaction can go. So ways to make sure that you get the E2 mechanism that you want is on page 297. And then there's some rules to pay attention to. There's Zaitsev's rule, which tells us the more highly substituted alkene is going to form. So if you look at the example here, you have the ability to create a double bond in two different spots, here and here. But as you can see, the more relevant product is the one where the double bond is interior, where it has more functionalities attached to the double bond, where in this case you have two methyls on this side and one on that side. In this case you have two hydrogens on this side and then two methyl groups or alkyl groups on the other side. So this one is more favorable because you have more substitutions to the alkene. Now with Hofmann's rule, you can dictate that. Now back up to the Zaitsev rule. The reason why you can do that is you're using a strong base, not a very big base, and some high temperatures. With Hofmann's rule, you usually get the less substituted alkene form. So in this case, you're using a bulky base. So that bulky base doesn't get interior. It stays to the outside and allows you to get the higher percentage of the less substituted form. So take a look at those and understand the differences and what conditions you might use to get one versus the other. And then another thing that's important is look at the mechanism of these, and if you understand the mechanism, then you can help you understand how the reaction goes. And one thing that's important is that this anti-coplanar geometry. So as you can see, in this case, you have this hydrogen is anti-coplanar to the chlorine. When that is set up that way, and you have this strong base, you can get this type of mechanism to happen, such that you're going to remove this hydrogen, create the double bond there, and get rid of the leaving group, the chlorine, in a classic E2 type elimination. So now, if we're dealing with secondary or tertiary alcohols, you can use acid catalyzed dehydration of alcohol to get to an alkene. So in this case, you're going to protonate the alcohol, make it a good leaving group, then it's going to leave in an E1 fashion. So E1 being that this is just going to come off and create a carbocation before the rest of the reaction happens. And the rest of the reaction is then a base pulling off the hydrogen that's next to it, allowing it to make the double bond, as you can see here. The dehydration of a primary alcohol is a little bit different. Since primary alcohols wouldn't be very favorable to make carbocations, it's going to go by the E2 mechanism. So in this case, the same first step, you're going to get some sort of protonation of the alcohol, but instead of the alcohol this water protonated alcohol just coming off, what happens is the base takes off the hydrogen in an E2 type mechanism, but you still get the alkene at the end. So depending on whether it's primary, secondary, or tertiary, you might have to use different mechanisms in order to get the desired end product. And so something to pay attention, I'm not going to spend a lot of time on it, but take a look in the reading, is the molecules will rearrange in order to become more stable. So in this case, you have a primary alcohol But later on, it makes more sense, or it's more stable, for that carbocation to rearrange in such a way to make it a more stable alkene, and it will do that. So take a look at the reading and try to understand what cases it might be that might happen. So then we get into alkynes, and we start talking about the acidity of terminal alkynes, because we could use them as acids, and we can see that those hydrogens can be pulled off. And then we talk about terminal alkynes as nucleophiles, and this is another lead into the next type of section, which is synthesis. So understand how you can use terminal alkynes to synthesize other molecules. And when we talk about making alkynes, what they talk about is this idea of vicinal dihalides. So you take an alkene, you add bromine across the alkene, you get two bromines. This is considered a vicinal dibromide. Then you use a very, very strong base, sodium amide, and you remove both of those through elimination reactions to get the alkyne. Okay, and it goes through the terminology of saturation versus unsaturation, so make sure you understand those terms as well. And then making and reacting alkynes. So in this case, we're getting to the reactions that can be used to add hydrogen across double and triple bonds. So in general terms, if you have hydrogen and a metal like platinum, palladium, or nickel, you can take the hydrogen and add it across a double bond to get an alkene. Alkane. You can do the same thing with the rhodium catalyst. Again, taking a double bond to an alkane. But in those cases, you really can't control when the reaction is done. As a matter of fact, they'll go until you get all the way to an alkane. But if, say, for example, you wanted to stop from an alkyne and stop at an alkene, you can do that with certain reagents, but you have to pay attention to whether you want a cis or a trans double bond. So in the case of using this P2 catalyst, you can actually take a triple bond to a cis double bond. But you can also use, in this case it's not stereospecific, but if you use the Lindlar catalyst, you can get a syn addition as well and get a cis double bond. And if you wanted to get a anti or a trans double bond from an alkyne, you can use this the lithium reaction or reagent, and you can get a trans double bond. So it's important to understand the difference. So you can use a P2 and Lindlar to get cis double bonds, and the lithium reagents to get a trans double bond from an alkyne. Then we get into organic synthesis. We're going to start organic synthesis early, so we can start talking about how to make different molecules, because that's kind of one of the big parts of organic chemistry, is making different things. That's how I come up with synthetic drugs and things of that nature. So this retrosynthetic analysis, take a look at that part of the chapter and see how that can help in the thinking of how you might get from a starting material to a target molecule. And of course, there's great summaries on page 329 and 335 and 336, and they kind of lay out all the different type of things we talked about throughout the chapter. So take a look at those. They're good. They kind of give you some of the summaries of the eliminations and some of the things to pay attention to. And this one talks about some of how you do some organic synthesis as well. So that's it for today. Have a good day, and see you in class.